Hello and welcome to lecture number 6. So today we are going to talk about few aspects or few characteristics of electrokinetic potential, which is zeta potential, and different types of electrokinetic phenomena. So we will start with very first essential type of electrokinetic phenomenon, which is electrophoresis. So before we begin, once again to refresh your memory, we have been talking about the zeta potential through the Stern model. So this is in the left hand side what I have drawn here. This is the Stern model, and you see we have a fixed layer of adsorbed ions. So these ions with the counter ions that get primarily adsorbed on the charged surface. So this adsorption is almost comparable like Langmuir's type of adsorption. So this is strongly adsorbed ions. So this is another fixed layer. So and we knew this is called the Stern layer. So potential here is psi d, and the potential at the charged surface is psi naught. And I also described earlier that due to the non-specific adsorption of hydrated hydrated counter ions due to some van der Waals interactions, essentially, that would lead to the surface of shear. So whenever this charged surface under an external electric force tries to move, it will move along with some types or some kinds of ion attached to it. So the movement where actually the charged surface gets separated from the rest of the solvent, so there is a shearing plane. So this plane is called slipping plane or surface of shear, and when the charged particle starts to move, the potential is measured right on this surface of shear. So the potential on this this wavy surface is denoted as electrokinetic potential or zeta potential. So that much we have learned earlier. So and this thickness, what I have drawn here, is inverse of kappa, which is the Debye length. So if I try to plot the potential once again, so you see at the Stern layer, at the Stern plane, the original charge potential would fall linearly, okay, because there is no distribution here. So this drop is a linear drop, okay, here up to this point to there, and from this point the rest of the ions are subjected to Boltzmann distribution, so it falls up. So you may argue that what happens in between, because between a Stern plane and the slipping plane, so there are some ions. So I would say that some approximation method has to be applied, because there is no perfect model on those loosely bound ions, due to some non-specific van der Waals interactions, how they are behaving. Of course, their concentration is obviously very high, and they are almost attached to the surface. So we have to accept that approximation. So I have to deal with it. So anyway, so when this potential falls exponentially wherever it intersects the plane of shear, so this here, this point, so whatever the potential we get, so I can draw one more line here. So this potential, okay, this is basically known as the zeta potential or the electrokinetic potential. So from this drawing, okay, you can see that there is a very little difference between psi d and zeta. So in general, so we can write in general, psi d, it's the numerical value we are talking about. Psi d is a little bit greater than the numerical value or the modulus value of the zeta. Okay, so this we will again observe in a few more instances. Okay, so the thing is, if we understand this picture, then there are two different scenarios, or probably two different extreme scenarios going to happen. So I'm going to talk about them one by one. So the first thing that I want to talk, that it is the reversal So let me. It is the reversal of the charge when we go from psi 0 to psi d due to adsorption of polyvalent counterions. So what happens is sometimes there are some multivalent anions. If you think that charged surface is positive, they get adsorbed, but since one ion means one unit of ion may have a multiple number of charges, so these are multivalent. Okay, so that means phosphates, PO4 3 minus, sulfate, so there are multiple negative charges. So what happens then? I'm trying to draw this picture once again. So this is basically a graph plot. So I'm going to draw. This is psi naught and this is psi d, and this is the surface of shear or slitting plane, and this is the thickness of the diffuse layer. So like this. So we started with a positive psi 0 here, but due to absorption of polyvalent counterions, the psi d can drop to the negative side. So this is 0. So this side is positive and this side is negative. So therefore we have a negative charge on the Stern plane. So that means the Stern potential is basically negative. So according to our understanding, we have a linear drop of potential from psi 0 to psi d. And after that, what happens? Owing to the Boltzmann distribution, the psi d would become 0 at the boundary of the diffuse layer following this exponential rise. So it would follow a curve something like this. So now here we will see that this level, okay, would be my zeta potential, and you see that its mod value would be less than psi d, or in other words, zeta potential would be less negative than psi d. Okay, and also we can think about the other extreme. So the other extreme is that here, in case it is the reversal of charge, but in the other case, we can say that adsorption of some surface active coions. So this is a very rare phenomenon, but it happens sometimes. So you see, this is the positively charged surface. So surface active coions means the ions will be having the same charge. That means here in this case it will be positive. So cations are getting adsorbed onto a positively charged surface. So this is a rare phenomenon, but it happens in some cases where those ions, due to some chemical interactions or chemical affinity with the charged surface, so they are called the surface active. So that means defying the electrostatic repulsion due to the Coulombic interaction, despite of that, it gets actively adsorbed. Okay, so then what happens basically? So I am again drawing the same diagram. So this is our basic motif. So whenever we talk about zeta potential, basically we have to draw such diagrams. So needless to say, this is the boundary of the diffuse layer. So here psi 0, we started with the positive one, so this is 0, this side is positive and this side is negative. So what happens here, that in a very peculiar manner, due to the adsorption of coions, the psi d becomes more positive than psi 0. So we have a here, so due to the more positive nature of the psi d, the potential increases linearly up to this point. So this is my psi d here, and after that the same thing, the potential will drop exponentially from here to here, so like this, and we have our zeta potential over here. Okay, so as you can see that in this case the zeta potential is less positive than the psi d. Okay, so with this kind of drawings, up to now, perhaps you can realize or even understand that the difference between psi d and zeta depends on two things, that is the thickness of this diffuse layer, and secondly whether or the thickness or the distance between this slipping plane and the Stern layer, and thirdly that what is the psi d and what is the difference between psi d and psi naught. So whether these are very closely positive or they are, you know, extremely opposite and with a very having a large amount of difference. Okay, so it all depends. But before we go further to show you a couple of more illustrations, let me tell you, well, perhaps I have told this thing earlier, that we can only measure zeta. Okay, so we can write that we can measure zeta experimentally, but we cannot measure neither psi d or nor the psi 0. But here psi 0 is estimated. Okay, so there are these two are different things. One is experimentally measured and another is estimated. So we know that psi d and zeta in normal cases, when barring from few exceptions, these are very closely related. And once we have measured the zeta, we have a faint idea, or rather we say that we have a considerable idea that how much should be psi d. And from psi d, we can take a guess of psi 0. Okay? We can make a guess, provided these are not extreme cases like absorption of surface active coions or absorption of polyvalent counter ions, etc., etc. All right. So, and one other thing is also that the exact location. So we said we should write here the exact location of the slipping plane, or in other words, the surface of shear, is not known. Okay, so experimentally it is not possible to know what's the exact distance from psi 0, but it is understood that it is situated at some distance from psi 0. Okay, it is understood from Stern model, and also of course it is situated further from psi d. So their appearance from left to right is basically psi 0 first, then there is some distance, there appears psi d, and after there is some gap, some distance, and there the slipping plane appears. Okay, so this is the basic model, and so I'm going to clean the board. I'm going to discuss two more illustrations where the zeta potential can be affected. So this the zeta potential depends on the relative location of this slipping plane with respect to Stern plane and the diffuse layer boundary. So let's clean the board and take a look at that. So let's take a look at these two examples, top and bottom. So here you see we have the identical distance between charged surface and the Stern layer, and also the distance between the Stern layer and the slipping plane is identical in top and the bottom, but the thickness of the diffuse double layer D1, and here it is D2, so you see D2 is much greater than D1. All right. So the question is, what would be the difference between the Stern potential and the zeta in A and B? So if you let's take a look at that. So let's assume that the Stern potential is just halfway between 0 and psi naught. So this is my psi d. So just halfway between psi naught and psi d. So therefore, we both would observe a linear drop between this point to this point. Fine. And then what would happen in both cases? It will follow the exponential fall. So in the first case, the fall would be sharp like this, and in the second case the fall would be exponential, but it would follow a much shallower drop at the initial segment, right? So the fall would be something like that. Okay, so it's like first order decay. So the higher the initial concentration, the decay would be initially would be faster. Anyway, so what we see now that here is my zeta potential zeta 1, and here, okay, in the next case it is my zeta 2, right? So now you see that zeta 1 is less positive than zeta 2, or in other words, the distance here, okay, so here the distance is delta 2 and here the distance is delta 1. So we can say that delta 1 is greater than delta 2. That means the difference between zeta and psi d is much more here than here. Okay, and also the zeta has been reduced, it is close to 0, but here it is not that much. So in which scenario we see reduced thickness of the diffuse double layer? So it's important whenever we have a strong electrolytic material, or when the ionic strength is very strong, we have a strong electrolytic medium, or the high concentration of electrolytic medium, I should say. So under high electrolytic concentration, and the thickness of the diffuse double layer seem to contract. So you will follow situation like this here. Anyway, so now let's consider another extreme, that is where the thickness of the position of the sleeping plane would vary. So how does it vary? I'm going to erase this example. I'm going to draw some fresh drawings and let's discuss. So we have another situation where you see the the diffuse layer thickness is identical both A and B. This is the psi 0 in both cases identical, and psi d assumed to be 50% of psi 0 in both cases identical. So we have to define the zeta potential. So you see, we follow the rule. So from here to here, it will follow the exponential fall like this, and the same thing here, it will follow the exponential fall like this. Okay. So now, the interesting scenario is in both the two cases, the zeta potential is different. For the first one, you see, this is the zeta potential, alright? And here, the difference is only this much, so we call it delta 1. And here you see, the zeta potential is here, far away from the Stern layer. So therefore, in this case, this is my delta 2. So this is zeta 1 and this is zeta 2. So the same thing here you see, where the sleeping plane stays farther away from the Stern layer, the zeta potential is close to 0, much less positive than this case, and the difference between the Stern potential and zeta potential is much higher than this case. So the question is how, what is the reason that this sleeping plane gets away from the Stern plane? So this happens due to some adsorption of non-ionic surface active agent. So in other words, it's called surfactants. Okay, so what happens that they screen the charges. So they are surfactant molecules. So we'll come to that later, what are surfactant agents. But they do not add anything to the potential because these are not charged, but they manipulate the presence of the sleeping plane. So due to that, this happens. All right. And so from these examples, you can say that unless the case is very special, that means due to some unusual activity like non-ionic absorption of non-ionic surfactant, absorption of polyvalent counterions or surface active coions. So unless or very strong electrolytic medium highly concentrated. So unless otherwise mentioned, apart from those special exceptions or special cases, one thing is very clear, that there is a very little difference between psi d and zeta. So therefore, in those general cases, if you can measure zeta, you can have an idea of psi d, and from that you can estimate psi naught. So this is all about the practical knowledge of the zeta potential, and we have avoided much of the theories or the mathematical equation related to this electrokinetic potential, Boltzmann distribution, etc., etc. So those are there in the textbooks. If you are interested, you can take further look at that. But for us, the chemists, this much of working knowledge is absolutely okay, as long as our knowledge is concerned on the colloids and surface chemistry. All right. So now we'd like to move on to electrokinetic phenomena. All right. So let's clear this out and start afresh. So we are going to introduce the concept of electrokinetic phenomena. So what is that? So let's first discuss about that. Suppose we have a medium. Okay, so just suppose we have a medium of electrolyte. So we have positive and negative charges all over, and the moment we place a particle, then if it is a charged particle, so let's assume that it has a negatively charged surface, and whatever the existing knowledge that we have, then we can expect that this particle will have a surface of shear around it. Okay, so I'm not drawing the star layer, etc. But whatever the knowledge we have gathered so far, so we can expect that the charge at this surface of shear would also be negative. Okay, so in this case, the zeta potential is negative, expected to be, because unless otherwise mentioned and unless there are charge reversals and all other exceptional phenomena, the zeta potential would have the same sign as of the charged surface. And on and around this zeta potential, of course, we have this diffuse layer. Okay, and then if we apply an electric field tangentially on the surface of that charged particle, so we assume that it is a spherical particle. So tangentially on the spherical surface, if we place electric field, so that means we would be applying an electric potential across the medium or across the electrolytic medium where the charged particle is situated. So this side is negative, this side is positive, just an assumption. Okay. So what is expected, that this particle would experience some electric force, and so this particle would then start to move towards the positive end according to this diagram. So when the particle starts to move, it would take along its whatever substance present around it with it, and we know that it can take the maximum substances, whatever is residing within the surface of shear. So that means from the surface of shear, the dislocation of the particle would start. So the dislocation of the particle with respect to the diffuse double layer would start at the surface of shear. So that's the boundary limit. So whenever this particle would start to move towards the appropriate electrode, so that phenomena is called the electrokinetic phenomena. Okay, or in other words, if the particle means okay, so whenever the movement of these charged particle or the ions, we call it electrokinetic phenomena, and there is a difference, or there are two categories. One is called the particle electrophoresis, okay, and the another thing is called the electro-osmosis. Okay, so let's write those terms. So one thing is called electrophoresis, and another term is called electro-osmosis. Okay, so let's define one by one. So electrophoresis is whenever this charged particle moves towards the appropriate electrode, so that is called electrophoresis. But you see, whenever we put the electrodes, there are ions, so therefore the ions present in the diffuse layer, so that means the counter ions, okay, positively charged, so that would move towards the negative electrode, and the co-ions would move towards the positive electrode. So as a result, there would be a flow of ions, so that means the electrolytic medium would undergo a net flow. Okay, so the movement of this electrolytic medium under application of external field is known as electro-osmosis. So this is the movement of electrophoresis means movement of charged particles, and electro-osmosis means it is the bulk movement of the medium, okay, under the external electric field. So the general definition of the electrokinetic phenomena is something like this. So before we define it, so let's try to understand. So here the charged particles are already there. Once we apply that electric field, something starts to move, either the particle or the medium. But it also happens that this is the charged particle and this is the electrolytic medium. If somehow the charged particle is made to move with respect to the medium, or the medium is made to move with respect to the charged particle, means charged particle remains stationary and the media moves, or the charged particle moves and media stays stationary. So there will be relative motion. So one moves this side and another moves this way. So this relative motion of the charged particle with respect to the medium would also generate some electric field or electric potential. So that also comes under this electrokinetic phenomena, and that's possible. So therefore the definition of electrokinetic phenomena is, we can write, it is the relative movement at the surface of shear plane. So that means if everything is stationary, there is no electrokinetic phenomena. But once the electric field is produced, so whenever this surface of shear gets separated from the rest of the medium, we call it electrokinetic phenomena. Or if we make the surface of shear to move with respect to the diffuse double layer, there will be production of an electric field. So that also comes under electrokinetic phenomena. Alright, so this actually is a big topic. Under this umbrella, we have both electrophoresis as well as electro-osmosis. So in this regard, we have to learn a few terms, okay, a little bit. So that means what is called electrophoresis, what is electro-osmosis. I think we have already discussed about it. We have a brief idea. And there are two other terms, that is called the sedimentation potential and streaming potential. Okay, so let's quickly discuss those terms before we move on to the topic of electrophoresis. Okay, so let's do that. Okay, so we classify the electrokinetic phenomena in this easier manner. So In electrophoresis, the moving substance is the charged surface, okay, or the charged particle, relative to the medium, that is the liquid, remains stationary with respect to this charged surface. Okay, so and this happens under an applied electric field. The same thing on electro-osmosis, but the thing is, here in electro-osmosis, the moving thing is the medium or the electrolytic liquid, where the charged surface remains stationary in relative manner, of course. Okay, so in both these cases, this happens under an external electric field E. On the contrary, so here what happens that in absence of any electric field, okay, so in absence of external electric field, if we keep the charged surface moving relative to the stationary medium, okay, then we would generate a potential, okay. So that potential is called sedimentation potential. So it happens like when a charged particle gets sedimented by gravity, automatically there will be a potential. So that potential is called the sedimentation potential. And here there is no external field is there. So in other words, when the moving thing is the medium, electrolytic medium, where the charged surface remains relatively stationary, then also we generate a potential, and that potential is called the streaming potential. Okay, and of course we have categorized already, there is no external electric field. So therefore, electrophoresis is related to sedimentation potential. Okay, so that means once the external field is applied, we see electrophoresis. But if the same movement happens without an external field, we get sedimentation potential. And under external field, if medium gets moving, we get electro-osmosis. And if the same movement is happening under an external field, we get the streaming potential. So these four terms are very important, and this we can understand in a categorized manner. The way I have put is a very simplest possible manner. So if we try to keep this picture in our mind, so things get less confusing. So now let's move on to the phenomena where under an external electric field we get the charged surface moving with respect to a stationary electrolytic liquid medium. So that means we are talking about electrophoresis. So in electrophoresis, or under the process of electrophoresis, there are three different phenomena. So number one is called the particle electrophoresis, or sometimes it's called the microscopic electrophoresis. And the second phenomena is called the moving boundary electrophoresis. And the third phenomena is called the zone electrophoresis. So, from the surface and colloids point of view, all these electrophoretic behavior are very important. So we are going to learn one by one. So first, start with the particle or microscopic electrophoresis. So let me take the board and discuss it. So let's first start with particle electrophoresis. So it's the most common type of electrophoresis, and it is one of the most widely applied technique as far as colloidal suspension is concerned. So what happens that I'm talking about the basic working principle. So there is a narrow tube. It can be a capillary, but little wider than capillary tube. With both ends, we have some platinum electrodes, and in the tube we have the colloidal solid. That means the charged particle under observation. So you see, I have demarcated two ends. Okay, and this is separated by a distance d. Usually d is in the order of 100 micron, and some electric field has been applied. Of course, you see that here if we apply the potential difference, depending on the charge of the particle. So let's assume here the particle is negatively charged, and it would experience the electric field E, and it would move towards the positively charged electrode. So usually what happens, that the movement of the particle is being observed by, so let's write, the movement is observed by a microscope. So when this technique was built, like at the initial era, the microscope that was being used, it was an ultra microscope. So the question is, what is ultra microscope? We will talk about that when we talk about the optical properties of colloids. But of course, this is not an optical microscope, remember. So using some microscope, the movement of particle is observed. So what is being recorded is actually the time t that is taken by the particle to move this distance d. Okay, so therefore, in other words, we record the velocity here. So this velocity is actually electrokinetic velocity. So this electrokinetic velocity, that means the speed of the particle under the charged under the electric field is equal to basically the distance d divided by the time it takes. So using a stopwatch. So in those days, people used to use a stopwatch to record the movement. But these days, these are all automated. We'll come to that later. So this electromagnetic velocity is equal to d by t. But this electromagnetic velocity is also related to electrokinetic mobility. So there is a quantity, it's called electrokinetic mobility, which is defined as mu subscript e. So this is equal to the electrokinetic velocity divided by the applied electric field, or the electric field is experienced by the particle E. So this is how the electrokinetic mobility is defined. Alright? And also, it was known that this electrokinetic mobility is proportional to the following things that I am going to write. That is the epsilon r. So epsilon r is the dielectric constant of the medium, means the electrokinetic medium or the electrolytic liquid, multiply epsilon 0. So epsilon 0 is the permittivity of the free space, okay, and then multiply zeta. So zeta is the electrokinetic potential, or the zeta potential, divided by eta. So the eta is the dynamic viscosity of the medium. So since we have a proportionality relationship, we can write, or mu A is equal to some constant C multiplied by epsilon r, epsilon naught, zeta divided by eta. So therefore, what happens is, we can equate these equations. So right from here, what we can write is mu E is equal to C multiplied by epsilon r, epsilon naught, zeta divided by eta. Now the same thing is equal to V over T. Sorry, the same thing here. mu E is equal to V over E. Okay, so V is nothing but d by t here, whole divided by the electric field experienced by the particle. All right. So if we do that, then therefore from here we can try to find an expression for zeta. Okay, so the zeta value becomes d multiplied by eta divided by t multiplied by e, and then we have c multiplied by epsilon r multiplied by epsilon 0. All right. So if we look at this expression, and then what we can think about that if the medium is fixed, then the kinetic viscosity or dynamic viscosity is fixed. So now the distance is specific to the equipment, so this d can also be fixed. So the electric field that is experienced by the particle is also a constant quantity, depends on the equipmental setup. C is a constant, and this epsilon r and epsilon 0 are also constant values. So therefore, the only varying thing here is the time t. So therefore, we can write this thing as zeta is equal to, so this thing here, distance multiplied by eta and all those things, is equal to a system constant. So this constant is specific to the equipment divided by time t. All right. So we arrive at a situation where once the colloidal suspension is placed in the tube, we just have to turn on the electricity to provide the electric field, and then we just have to count the time the particle takes to move from point A to point B, which is already fixed. So by recording the time t directly, we can measure the zeta potential. So that is the working principle for particle electrophoresis, or also called the microscopic electrophoresis. So these days, okay, we do not use this ultra microscope to see the movement of a particle within a capillary tube. So these days, advanced automated zeta potential measuring equipment is available. So one of such equipment, probably you have heard about it, or you have seen it, or you are going to come across, is manufactured by the company Malvern. So this is a trademark name. So it's called the Malvern Zeta, or we can say Malvern Zeta Potential Analyzer. So it's also called the Zeta. Anyway, so there, instead of an ultra microscope, they use some automated laser Doppler effect. Okay. So this is based almost like the principle of ultra microscope, but it's depending on the laser mediated Doppler effect to follow the particle, to track the particle movement, and the rest of the things are the same. So but one added advantage for this using this laser Doppler effect, this Malvern Zeta also reveals the hydrodynamic diameter of this particle. Okay, and that is done by the light scattering experiment based on Tyndall effect. So we'll come to that effect later. So it's all possible to use due to the use of this laser Doppler effect. So using this Malvern Zeta Potential Analyzer, you can get to measure not only the zeta potential of the particle, also the different particles size distribution through the dynamic light scattering experiment. And so in this working principle, the one thing is how to know E. So remember, E cannot be directly measured because E is the field experienced by the particle at that condition. So there is a formula, okay, by which E can be measured. So this is expressed as I over K naught divided by A. So the definitions of this, that I is called the electrophoretic current. So that can be measured by the instrument. So it's called electrophoretic current. It can be measured. And K naught is the conductivity of the dispersion. And this can be measured separately. So you take the medium and the K naught can be measured. And in fact, these days, okay, so let me talk about AA is the cross section of the tube. So these days, everything is so automated that we don't have to do anything. Everything, the electrophoretic current or the conductivity of dispersion cross section can be instantaneously determined by the machine. We do not have to do anything. We just have to put the colloidal dispersion in a sample chamber, and we just have to turn on the measurement switch. It will just take a few seconds and it will give the data, that is the zeta potential. But of course, it is measured through this working principle. It only measures the time of movement for a particle undergoing electrophoresis, movement of particle from one end to another with the effect of the electric field, and that will tell us the zeta. And remember, from zeta, we can take a guess of stand potential and more importantly, the potential at the charged surface. So that's what we started the topic 2 lectures ago. Anyway, so we stop it here at the particle electrophoresis. And next we will move on to the moving boundary electrophoresis, and then finally another very important phenomena is called the zone electrophoresis in terms of protein colloids chemistry is concerned. So I will see you in the next lecture, lecture 7, with the remaining parts of the electrophoresis. So please follow the textbooks along with the lectures to understand everything clearly. And so till then, see you in the next lecture. Goodbye.